Okay, so again, we're going to assume that we're using a second order Taylor polynomial for our approximation function. And we're also going to assume that we're using the constraint on the for the trust region, right, in our approximation. Now, we need to solve the optimization problem, the constraint optimization problem. And actually, this problem becomes very easy to solve. It can be solved in a closed form solution if the Hessian matrix H is a positive or definite or positive semi-definite matrix. Then it's either convex or strictly convex, and we can find the global optimum or one of the global optimums, right, in a closed form way. However, this is usually not the case in many practical problems, right? And in many practical problems, the Hessian matrix is not positive semi-definite. It's not a positive semi-definite matrix. That is, we have a non-convex optimization problem to solve. So we're going to use gradient-based approaches that guarantee improvement per step. And we're going to find the local optima within the trusted region. So how can we define this non-convex optimization? So we would like to solve some loss function, to minimize some loss function subject to the constraint, right? Again, we would like to, in our case, we would like to maximize J, or to minimize the loss function that is defined over J. I will define it in a second. With respect to the policy. So we'd like to find the policy that optimizes J, the expected sum of return, within some trusted region of our current policy, the policy that we're currently considering. So let's start by defining an appropriate loss function, and then we'll minimize that loss function, right, for a well-defined optimization problem. So what is our loss function? Specifically, if we go back to the policy gradient theorem, what is the loss function that is assumed behind that we can define over the policy gradient theorem? So we'll have to work backwards, but let's look at that for a second, right? So if we would like to perform policy gradient on some kind of a loss function, right, on the appropriate loss function, we'll update our policy to be the current values plus some step size times the gradient in our loss function. Okay, so first thing to do is to define the loss function that we would like to minimize. So previously we said that we would like to maximize the J, the expected sum of discounted the expected return over a specific policy, and we would like to increase this expected value. And more than that, when we saw the policy gradient theorem, we also saw how to approximate the gradient of J at any specific point, for any specific policy, right? The interesting thing here is that we can work backward and take the integral of that in order to get a specific loss function, right? And you can easily do that by, well, taking the integral of this function, and we get a loss of the loss function that is appropriate for the policy gradient theorem. That is, if you take the gradient of this loss function, you get the policy gradient as we defined before. Now, we can actually take this a step forward, and instead of considering this type of policy gradient, right, the one that is the advantage function times the gradient of the log of the probability of the log pi, log of the probability of selecting a specific action at a specific state, we can also define the gradient of the natural logarithm as the gradient of the policy over the value of the policy at the specific point for the specific action and state, for the specific action at the specific state. And we can further write that as the gradient of the policy that we're trying to adjust over the old value, the fixed value from before. Why can we do that? Because we consider this, the bottom value, as fixed. We consider theta old as fixed. And now again we can take, and this is just a different version of the policy gradient, right? And we saw that before. But if we take the integral of this type of policy gradient, then we'll just, also in the original paper, this was defined as the loss IS. IS stands for important sampling, because you can see here that what we get is a loss that is defined over as the advantage function multiplied by the important sampling ratio, as we've seen before, right? The policy that we're trying to, that our target policy, over our behavior policy, the one that we use to actually sample or collect samples from the environment. So as I said before, we consider theta old as constant, so we can do this step here, and also this is exactly the important sampling ratio that we saw in slide deck number 4. And actually that makes sense. We can actually reach to the same conclusion if we try to look at this problem from a different perspective. So what are we actually trying to do when we compute the new policy? We're actually trying to maximize the advantage over the old policy, right? So the best new policy would be the one that has the highest advantage over the previous policy, right? However, we don't observe this specific state and actions from the new policy. Instead, we have state and actions from our old policy. And this is why we can't just compute the advantage function over state and actions that we don't see from the optimized policy. We don't know that policy, we don't have access to it. We just have access to the old policy. This is why we need to multiply the advantage function by the important sampling ratio. And this is still a correct estimation of the advantage function at our target policy. For the full proof, you'll have to go back to slide deck number 4. We had it there, we discussed it there. So we saw that we get to the same solution using two different logical arguments, which makes sense. Hopefully it makes sense, right? So we reached it both from a top-down method, just by looking at the objective that we actually care about, but we also derived it from the policy gradient theorem, which is kind of crazy. Everything connects back to the same point, which is usually a good indication that the math is correct, right? We're getting to the same points. So there is still an issue with the important sampling loss. And the main issue is that, well, at the end of the day, it approximates the performance difference between some target policy, the policy that we're trying to converge on, or the optimal policy that we're trying to find, and the behavior, our current behavior policy, the pi old, our previous policy, the one that we used to collect data from the environment. And as we've seen before, we saw some example with important sampling ratio. The closer the two policies, the target policy and the behavioral policy are, the less variance you have in your estimation. Right? The more accurate your estimations are. And again, that ties us back to trying to somehow bound the difference between the two policies, the target policy and our behavior policy. When the two policies are far from each other, then the loss approximation, the loss important sampling approximation, LIS, is usually untrustworthy. And this is why we would like to keep these two, the target policy and the behavioral policy, the current policy, are close to each other. And so we define the following trust region update, the following optimization problem. So again, we would like to maximize our loss function, the loss function that we've seen before, right? Subject to the following constraint. By the way, the maximization here is maybe, so we either want to maximize or minimize. I'm sorry for the, sometimes we switch between these. The original paper considered costs, while mostly in reinforcement learning we consider reward. Costs you usually want to minimize, reward you usually wants to maximize. So don't pay too much attention to the max or mean here. Just think of these as optimum, finding the optimal. It can be either max or mean. But now we add a constraint. So how can we constrain two policies? And I'll just remind you that the policy defines, source policy defines a distribution over the action space for each given state. So we discussed this before, right? Hopefully you remember. What loss function is appropriate to define the distance between two distributions?
KL divergence.
KL divergence, right? We discussed it before and I told you we'll revisit it. So KL divergence is indeed an appropriate loss function or appropriate distance. It's not a distance measure, but an appropriate way to measure similarity between two distributions. Okay, so indeed, we set our trust region based on the KL divergence between the two policies. And of course, our policies define a distribution over all of the actions for a given state, well, and a given policy, right? And the given policy parameters. That is, we would like to find the best next policy based on data from the current policy while bounding the distance between the policy's distributions, right? Through KL divergence, bounding the KL divergence. Off-policy estimations that are based on important sampling are usually noisier the further they are from the behavior policy, hence the necessity of bounding the change. Again, if you don't intuitively understand that, go back to our fourth slide deck. I actually showed you a running example where we used important sampling. And actually once we used, you can see there, in one of the examples we used two policies that are significantly different from each other, and then we saw very noisy updates using the important sampling ratio, which we kind of mitigated by using the normalized version, but that introduces bias, and well, we had that entire discussion before. The important thing to understand is if we use important sampling, we have to somehow keep our two policies close to each other, else the estimations become very noisy. Finally, the constraint on the KL divergence can be written as a penalty in the objective function, right? And then we have a Lagrangian. So we have the objective function is our loss IS, as before, we'd like to optimize that, minus some beta, some Lagrange multiplier, times our constraint. Okay? And you might ask yourself, well, is this exactly the same as having constraint optimization? So we won't go over Lagrange multipliers, but this is exactly what the method of Lagrange multipliers tells us. It tells us, and you're more than welcome to go over that by yourself. I won't do this during this lecture. But the bottom line is that for any small delta, for any bound on the KL divergence, there is a specific beta. Sometimes it's hard to compute what is the specific beta, but there exists a specific beta value such that both approaches results in the exact same optimality point. Okay, again, it follows from the method of Lagrange multipliers. You're more than welcome to read about that by yourself.